Okay, so in this video we are looking at summarizing Unit 4.8, okay, which is our further organic topic. So we are looking at chirality, the new type of isomerism that you've met, stereoisomerism, okay, the reactions of carbonyl compounds, how you tell the difference between aldehydes and ketones, how you identify carboxylic acids, what carboxylic acid derivatives are, and what their reactions are. Okay, so the first thing we wanted to review was to look at the isomerism that is possible in a carbon-carbon double bond. Okay, so we've got an example molecule there. So for this example, my red atoms are oxygens, my white atoms are hydrogens, my black atoms are carbons. Okay, so it's not possible for me to rotate that double bond. Okay, so I can't get this oxygen, this right-hand oxygen, and this left-hand oxygen on opposite sides without breaking the bonds. Okay, so if I wanted to get it on the other side, I would have to break the bond and then reform it again. Okay, and obviously that takes energy to do that. Okay, so I will have two distinct isomers where they're on the same side or where they're on the opposite side. Okay, and in year 12 we learnt how to name these. If they were on the same side, they were cis, and then if they were on the opposite side, they were trans. Okay, and it's the fact that in your double bond, you can't rotate around that double bond, whereas in a single bond, you have free rotation. So they can be either on the same side or opposite sides, so they are not isomers of each other. Then we looked at what happens if my two groups are different to each other. So in this example, where green is a chlorine and the red is an oxygen group, okay, how do I name that? Well, now we're looking at using AZ nomenclature, okay, and we're looking at if we need to give each group attached to the carbon a priority, and we do that according to atomic number, atomic mass. Okay, so chlorine's got an atomic number of 17, an atomic mass of 35. Oxygen's got an atomic number of 8, an atomic mass of 16, and each of the hydrogens have an atomic number, or atomic mass of 1. Okay, so my chlorine and my oxygen are on opposite sides, so we look across the plane of the double bond. Okay, so my chlorine and my oxygen are on opposite sides. So when it's opposite side, it is an E isomer. Okay, and the other isomer, where the red oxygen would be on the same side, would be a Z isomer. Okay. And we're moving on to look at an existence of optical isomerism. So in the what a chiral center means, okay, what an asymmetric carbon means, okay, and what a non-superimposable mirror image means. Okay, so we've got the idea that in my keywords, I've got a chiral molecule. Okay, so a chiral molecule is one that will have 4 different groups attached. Okay, and that will be my chiral center. Okay, and obviously I can show this image in 3D, so I can have one bond coming out of the page, one bond going behind the page, so it's in 3 dimensions. Okay, and I can look at drawing a mirror image of that molecule. Okay, and Okay, my mirror image would be non-superimposable. So what I mean by that is, if I had my first group attached, okay, there is no example where I could simply rotate that round and have a different, and have the same isomer. Okay, so if I take the example of this molecule, okay, that central carbon is my chiral carbon. So it's got a chlorine coming out of the page. Okay, it's got a hydroxy group in the plane of the page, this hydrogen in the plane of the page, and this group at the back of the page. That's a bromine group. Okay, so that's going to be a chiral center, and I could build the exact mirror image of that. Okay, so I could have my hydroxy group, okay, pointing downwards. I could have my chlorine group pointing upwards. Okay, I could have my grey group pointing to the back. Let's take one of these grey atoms. Okay, and I can have my hydrogen in plane. Okay, so that is going to be my mirror image, and you can see that there's no way that I can flip those two molecules and make them fit over each other, because now in the second one my bromine atom is in a different place to where it was in the first one, so there's no way I can put those on top of each other and they are the same molecule. They're different molecules. So that's what we mean by optical isomers. They are non-superimposable mirror images. Okay, so we can move on to section C, and we can identify these mirror images as being able to rotate a plane of polarized light. Okay, so if I hit this enantiomer with a plane of polarized light, depending on which enantiomer it was, it would rotate the light either clockwise or it would rotate it counterclockwise. Okay, if it is an R isomer, it's going to rotate it clockwise. If it's an S isomer, it's going to rotate it anti-clockwise. Okay, and the way that we look at whether it is an R or S isomer, we look at the priorities of each of my groups. Okay, so I do that from atomic mass. Okay, so I artificially put hydrogen, which is the lowest priority, to the back. Okay, so I've got bromine, which is my heaviest, then chlorine, which is my next heaviest, then my hydroxyl group at 17, which is my next heaviest, then my H group. Okay, so it's going that way round, which is counterclockwise. So that is an S isomer, and then this one would be your R isomer. Okay, and just to show that that's where my bromine group was attached. Okay, so I've got bromine, chlorine, and oxygen, so that's going clockwise round. Show it better there. That's going clockwise round, so that is my R isomer. Okay, so I can name them as R and S isomers, as optical isomers of each other. Okay, and we can look at, on the optical activities, okay, predicting whether a molecule is going to react via SN1 or SN2 on the addition to carbonyl compounds. Okay, so we've got a carbonyl compound, and depending on what the addition is or the substitution is, Okay, we need to be able to predict whether it's going to go SN1 or SN2. Okay, so SN1 you will get both optical isomers. So both R and S, and you will get 50% of R and 50% of S. Okay, so the overall effect, well, 50% of R is going to rotate at 50% clockwise, then 50% S is going to rotate at 50% anti-clockwise, so the net effect is 0, no rotation. Okay, whereas SN2, you're going to get an inverted stereochemistry. Okay, so my nucleophile is going to come in and it's going to invert the stereochemistry of my carbonyl group. Okay,